Hey, this is Mike. This video is part of the A-level series where I talk about core concepts and sometimes more niche concepts. In this video, I'll be talking about permutation and combination. When I say permutation and combination, I mean the ones which can be found by these two formulae. Before I begin, I would like to make it clear that I'm going to develop these formulae from ground up. There is nothing wrong for accepting the formulae and be able to apply them, but there are benefits from knowing how they came to be. If you are interested, welcome aboard. Throughout the video, I'll be using these 5 balls labeled from A to E. Let's begin by asking ourselves this fundamental question. How many ways can we order these balls? Technically, we are just counting them, but we need a way to do this systematically. Imagine using 5 holders for each ball we will draw. For the first ball, we have 5 options, thus the number of permutation is 5. If we choose ball A for the first draw, we will then have 4 options for the second draw. Since this is true for any ball we could choose for the first draw, we should then have a total of 4 times 5 equal to 20 permutations. For every permutation we have after first 2 draws, for example A and B for the first 2 draws, we have 3 options for the third draw. The total permutation becomes 5 times 4 times 3, which is 60. This pattern repeats until we have drawn all 5 balls and the total number of permutation is 120. The way we get to 120 permutation is by 5 times 4 times 3 times 2 times 1, which is quite mouthful, right? So we have invented the notation factorial, which is just 5 with an exclamation mark. I believe you can see that 5 is just an arbitrary number I've picked. The previous discussion applies to whatever positive integers we may choose. So in general, if you want to find the number of permutations for n distinct objects, we just need to do n factorial. However, I do want to highlight why the objects need to be distinct or the formula won't work. For our 5 balls example, let's just swap ball B with another ball A. Now 2 balls are indistinguishable from each other. To illustrate the idea, let's just first color these 2 ball A. When we draw the balls in order, we could end up having one scenario where we first draw the yellow ball A and then green ball A, while in another scenario, we first draw green ball A and then yellow ball A. However, let's not forget, we add the color ourselves. In reality, they are not distinct. They represent the same permutation. Therefore, if we have repeated objects, n factorial will overestimate the number of permutation due to double counting. The next question we are going to ask is, what if we only take some balls randomly from this set and order them? Let's see how it works when we want to order 3 randomly drawn balls out of 5. Interestingly, some of you might have realized we already have the answer. This is the answer when we order all 5 of them. However, if we go back in time and stop right after drawing the third ball, that's the answer for our new question. We have 60 ways of ordering 3 randomly chosen balls out of 5 distinct balls. Now we want to do something algebraic. We want to change the way the answer is presented by rewriting it into 5 times 4 times 3 times 2 times 1 divided by 2 times 1. The reason is obvious because we have a neat way to represent them, which is 5 factorial divided by 2 factorial. When we think about it, this number 2 has a physical meaning, which is the number of balls we leave out. So we will rewrite it again into 5 factorial divided by 5 minus 3 factorial, and this is what the formula permutation NPR will give. In general, the number of ways of ordering R objects taken randomly from n distinct objects is given by this formula. One thing I need to remind you is by definition, 0 factorial is 1. I can explain that, but to make the video more concise, I've chosen to omit it. We will see in an example why this is needed. Let's say we want to compute something we already know. That's the number of permutations for ordering 5 balls out of 5. We already know the answer is 120, but if we apply the permutation formula, we'll see at one point we need to evaluate 0 factorial. So please remember that 0 factorial is 1. The final question we will ask ourselves is, how many weights can we choose these balls if we randomly take 3 out of 5? What I mean by choosing is that we don't care about the order they are chosen. We only care about what are chosen. To illustrate the idea, let's consider the scenarios where we will get ball A, B, and C. If we continue using the permutation weight of ordering, there are a total of 6 permutations that will get us ball A, B, and C. However, we don't care about the order now. In other words, these 6 permutations correspond to just one combination. When we think about it, this phenomenon doesn't just apply to combination ABC. It also applies to other combinations like ABD and ACE. So every 3-ball combination has 6 permutations. To account for this duplication, we need to divide our number of permutations by 3 factorial, which is 6. We'll see that the number of combinations ignoring the order is 20. Only 1/6 of the number of permutation if we consider order. If we directly apply the combination formula, we'll get exactly the same result. To conclude, if we want to find the number of weights of choosing R objects taken randomly from n distinct objects, we use this combination formula. This concludes our video, and I hope you have gained an understanding of how the permutation and combination formula came to be. As always, thank you very much for watching. Please like and subscribe for more maths content and study tips in general. See you soon.